Hello! In this video we'll be going over what you'll be doing in Experiment 6, which is your Introduction to Spectrophotometry, the absorbance spectrum of Allura Red. The objectives of our experiment are for you to determine the lambda max of Allura Red, which is a food dye, to construct a standard curve for that Allura Red, and to then consider and determine the concentration of an unknown solution of some commercial product with that food dye using Beer's law. This experiment will help you develop some skills. One, you'll have some familiarity with using and cleaning cuvettes, which is a very important part of using a spectrophotometer. Then you'll have experience using volumetric flasks and pipettes, because a large part of this is making sure that you can accurately produce serial dilutions of known concentrations. With that, then you'll have the following knowledge. You should understand the measuring range that's required in spectrophotometry and how it's used experimentally. And then you'll have expertise in generating a standard curve and knowing how it's used, especially for today, determining the concentration of a solute. Now the electromagnetic spectrum has light with multiple frequencies going from gamma rays all the way to radio frequency, and we can use lots of these types of EM radiations for different purposes in the chemistry lab. Today we're going to be focusing on the very, very narrow window of visible light that has this region from about 400 to 750 nanometers. And you might be familiar with this, knowing that 400 nanometer light is that purple light, and as you go across to 750, that's red light. This is what we're going to be focusing on today, is how we can relate the fact that there's going to be things that we use regularly, both in our lives and in the chemistry lab, that appear to have color. And they have color because they're absorbing some light and not absorbing others. So very classically, plants are capable of photosynthesis, and they absorb specifically blue light and red light. And they appear to be green or yellow to us because they're not absorbing those wavelengths from 500 to 600s. But they absorb the light in the mid 400s and the mid 600s. And that's why, again, it looks green, because it's absorbing the red, it's absorbing the blue, but it's not absorbing greens and yellows. And we'll take advantage of that for solutions. So potassium permanganate in solution is purple, and the idea is that as white light passes through the solution, some light's absorbed by the permanganate and other light is transmitted. The thing to remember is that the absorbance of any solution depends upon not only the solute, but also the wavelength of light, the concentration, and the path length. Seeing the permanganate ions in the solution, it's pretty clear that there's a dependence on the path length, because the bulb here is wider than the neck, and you can see that the bulb looks quite pinker than the neck does, and that's because the absorbance of the light depends upon the distance it takes to pass through, so this path length is much shorter in the neck. So this lab is all about getting you used to using a spectrophotometer. And the general idea of spectrophotometry, at least how to use it in the lab, is kind of simple. What you'll do is you'll have a cuvette. That's kind of this very special piece of sometimes glassware, or usually sometimes it's a cuvette. Our cuvettes are made of quartz normally. We'll be using plastic cuvettes. You add a solution to that cuvette, you place it in a spectrophotometer. The spectrophotometer will then vary the wavelength of light and vary the transmission of light, which will relate to the absorbance. If more light is transmitted, then less light is absorbed. If more light's absorbed, then less light is transmitted. And the key ideas to remember is that if you see light that's transmitted, that means that light was not absorbed. And the only color that we see is because of any transmitted light that was not absorbed. A spectrophotometer itself is not so simple, however. The way it generally works is that there's some light source that produces the electronic radiation that we need. There's a slit that then narrows and aligns the beam, that then passes through a prism, and the prism can rotate to then select the wavelength of light that we want. That single wavelength is then isolated using another slit that passes through our sample, And then there's a detector that measures the light that was transmitted. You can see that there's more light here than what made through, so some of the light was absorbed. The detector then turns that into a signal that the computer can display. Modern spectrophotometers can detect and measure multiple wavelengths of light simultaneously and continuously. Other ones, like the ones we'll be using, are simpler and much less expensive, and generally only measure one single wavelength at a time. Now, what is the purpose of using a spectrophotometer at all? I mean, what benefit do we get by seeing if light's absorbed? One thing is that if you know which wavelengths of light are absorbed, we know something about the structure of the molecule. Because if there's a light that's absorbed, it's usually because we're exciting electrons that are in the sample, if we're talking about in the visible range. So knowing the wavelength of light lets us know something about these energy levels, and it can help us learn things about the molecules themselves. But for us, we're going to use it to determine the concentration of an unknown. So you remember earlier that we determined the concentration, effectively the mass of sulfate in a mixture, and you saw how long it took to go from the mixture to having our final compound. The benefit of spectrophotometry is that it's quite quick, it's quite accurate, and it's relatively cheap because absorbance is directly proportional to the concentration. So you can have a mixture and easily determine the concentration of a solute in a solution. So that's what we're going to do today. The goal at the end is to take a commercial product that has this food dye in it and determine the concentration of that molecule in something like Gatorade. But first we need to prepare for that. So first you need to find out what the lambda max, the wavelength of light that our food dye will absorb the most light. Then we'll consider constructing a standard curve so we can then figure out what the molar absorptivity of Allura Red is. And then with those two things in hand, then we can determine the concentration of an unknown. So here's a spectrum of the various absorption versus wavelength of a solution of potassium permanganate. So if you see, the absorbance goes down around 400 nanometers and then has this maximum around 500 to 525 and then falls off again. It doesn't absorb much in the 600 to 700. So remember, this region is blue, this region is green and yellow, and this region is red. So if it's not absorbing blue and it's not absorbing red, that means that the color of the permanganate appears purple to us. And if it's absorbing 525 nanometers, primarily, this is the lambda max, the highest absorbance it has. It's absorbing green light, it's not absorbing blue or red, and that's why this looks purple to us then. So remember again, the lambda max is the wavelength at which the absorbance is the greatest, and this depends upon the solute. Now, you're going to be doing that for Allura Red. You'll place that solution in a cuvette and place that cuvette in the spectrophotometer. You'll measure the different absorbances of the solution across a range of wavelengths, and then the LabQuest 2 will then show you that absorbance versus wavelength plot, and that's what you'll need in order to determine the lambda max of your food dye Allura Red. Once you know that lambda max, that's the wavelength that we'll use for our standard curve. We'll get the most sensitivity, because you can imagine that the more absorbance we have, then the more sensitive we are to changes in concentration. So once you determine the lambda max of Allura Red, we'll construct a standard curve. And this is because even though you could technically determine the molar absorptivity, that ratio that allows you to relate the absorbance to the concentration, you could determine that from one single point, but you'll get more confidence and you'll reduce your error if you construct a standard curve and you measure the absorbance versus concentration over a wide range of samples. One thing to consider is that for our standard curve, the absorbance cannot be too high or too low. And usually you'll only discover this through trial and error. We'll try and guide you to be sure that you know what concentrations you need in order to do this quickly. But just to kind of illustrate this idea, here's two solutions of potassium permanganate, and you can see one is very, very purple and one's just lightly purple. It's very difficult to quantify the amount of light that will pass through this sample because of how concentrated it is. There's going to be very little light that passes through. So we know it's a very high concentration, and if very little light passes through, it's going to be very hard to quantify the concentration. The same thing happens if it's very dilute. If there's very few molecules to absorb the light, it's again difficult to determine the concentration. So we have to kind of find a sweet spot where the absorbance generally falls between about 0.05 to about 1.0. That's kind of the best range for a spectrophotometer. So what you'll do is you'll take a stock solution of known concentration, and then using your volumetric flasks, prepare solutions of various known concentrations, always measuring the absorbance at the lambda max. So here you can see here's a series of solutions, all varying concentrations, and you can see pretty clearly that there's also different colors of these solutions as well. So this is effectively what you'll do. You won't have this many volumetric flasks, so you'll have to prepare your solution and then pour it out so you can do another dilution. The general thought is that you're going to plot the concentration of your solute versus the absorbance that you detect. And here you can see you can do this a number of times, and then if you plot that concentration versus the absorbance, this is then what gives us what we call then our standard curve to help ensure that we get the most accurate reading for our molar absorptivity. Now the straight line, as you remember, has a general equation of y equals mx plus b. We're going to relate this to the idea of Beer's law, where absorbance equals the molar absorptivity times the concentration times the path length. So the idea is that if you have the absorbance on the y-axis and the concentration in molarity on the x-axis, you'll then use your best fit to determine the value of the slope. You know the path length, that's the dimension of the cuvette, and the cuvettes are 1.00 centimeter. You'll then find the molar absorptivity of Allura Red, and those will have units of per molar per centimeter. And that's because your x-axis will have the units in molar, and our path length is in 1 centimeter. I want to also just point out again that the molar absorptivity is dependent upon a huge number of things. It's namely dependent upon the substance, as well as the wavelength that you're testing it at, but it also will change if you change the temperature and the solvent. So this really is specific for your experiment that you're doing. So once you have your plot, remember again, the Beer's law is that the absorbance equals the molar absorptivity multiplied by the path length multiplied by the concentration. And if you plot the absorbance versus the concentration and fit it to a straight line, what we're doing is we're considering that the y-axis is absorbance, the x-axis is the concentration, which means then that the slope is the molar absorptivity times the path length. And if we know the path length, then we can then determine the molar absorptivity. The b of this equation should be 0, but it doesn't have to be 0. So don't assume that it is. We'll actually have to see that and test that for ourselves. So to make your standard curve, the stock solution of the Allura Red that you'll have is about 4.0 times 10 to the negative 5 molar. It's important that you write down the actual number. You'll want to have 8 solutions in your standard curve, where one of them will be water alone, which you'll consider to be 0.00 molar. You'll also have, we'll call that your blank solution. And then another one will be the stock solution. That leaves then that you'll need to make another 6 solutions, and you're going to prepare those to be various concentrations by diluting your concentrated stock solution. These dilutions should be kind of evenly divided across the range that you'll test. So remember again that the stock is about 4.0 times 10 to the negative 5 molar, and that'll be your highest concentration. One hint that I'll give you is that the standard with your lowest concentration should be somewhere between 2 and 4 times 10 to the negative 6th molar. So I would do some math to figure out how you should do these dilutions to get you 6 more concentrations between 0 and 4 times 10 to the negative 5 molar, with the lowest one being somewhere between 2 and 4 times 10 to the 6th molar. Then once you have that, figure out what those concentrations are in molar and then in micromolar, in micromoles per liter. Once you have all of these stock solutions, you'll measure each. You'll measure their absorbances at that lambda max value. Then you'll use the lab quest to construct your standard curve, determine the slope, and once you have the slope, you can then solve for the molar absorptivity. Now, once you have your standard curve, now we're prepared to determine the concentration of our unknown using our Beer's law. So you'll find that Allura Red is in lots of different things, and if it's some kind of unnatural red color like you see in the Kool-Aid, in this mouthwash, or in Mountain Dew, it likely has this food dye in it. And the idea is that once you have your standard curve, where you have a standard at a certain concentration and you measure the absorbance, and you do this enough and you have this straight line, you know that the Beer's law is consistent across this range. The rule that absorbance is proportional to the concentration is always true as long as it's within these range of values that you've tested. At some point, Beer's law is no longer true if the concentration is too low or too high. So it's important that if you get an absorbance value of this unknown, that absorbance then falls within absorbances of your standards. If it falls outside of it, we're going to have to do something to fix that. So guaranteed, your absorbance is going to be too high. It's going to be outside of your standard curve. So what you're going to do is you're going to take 15 milliliters of your unknown sample. You'll use your pipettes, either the 1 or the 2 ml pipette, to accurately move that volume into a 10 milliliter volumetric and perform a dilution. Then you'll measure the absorbance, and if you do this correctly, then the absorbance will fall within the absorbances of your standards and your standard curve. With that, then you can determine the concentration of your diluted sample, and from your diluted sample, you can then calculate the concentration of the undiluted sample. One good thing to do is not just as soon as you get one value that falls in the range, then calculate what that concentration is. You should likely do this multiple times, doing different dilutions. Because the standard curve can give you such a wide, there's such a wide dynamic range that you can determine the concentration, and you'll get better data if you do this multiple times. If you get a value, say if you dilute it 10-fold, I would then dilute it again to 20-fold or something like that. So you can get that absorbance multiple times and get some average and standard deviation and confidence in what that concentration of the undiluted sample is. Remember again that the dilution calculation is going to be your friend. So we don't know the molarity of our unknown. With Beer's law, we can determine the molarity of our dilution. And if you dilute 1 milliliters into 10 milliliters, we'd call that a 10-fold dilution. That means that the concentration then is 10 times higher than your diluted one. Or if you do 1 mils in 20 mils or something, then that's a 20-fold. If you do 2 mils in 10 mils, that's a 5-fold dilution, which means that it's 5-fold concentrated. So you're going to be doing a lot of dilution calculations across this lab. Finally, just some notes about what you should know for the lab. First of all, remember that you're not going to have enough volumetric flasks to hold all of your dilutions. So what you'll do is you'll make your dilutions and then eventually move them to clean and dry and labeled beakers to keep track of each solution. It's a good idea that you stop and show your absorbance data before you discard anything, in case if you have to redo any of your absorbances. It's important then that we can help you, because it's easier to check the absorbance again than it is to make a solution again. The cuvette has two sides to it. One has these ridges, and one is transparent. And it's important that you put the cuvette in the correct way. And before you start, it's a good idea to check to see exactly where the light is coming from and where it's entering, to be sure that when the light passes through the sample, it's passing through the transparent sides and not through the sides that have these ridges on them. Other important things to remember is that it's pretty easy to get a droplet on the outside of the cuvette, so be sure to wipe that down. Next, also be sure that you rinse the cuvettes well. You will want to rinse the cuvettes with the next solution that you're going to test. So add just a ml or so of the solution, and then dump that, and then add another ml to rinse the cuvette, and then dump it. So that way you don't have any remnants of the previous solution, because any extra drops from the previous one will change your concentration. It's also very easy to have air bubbles in your sample, so make sure that you don't see any bubbles that will get in the way, because any air bubbles then changes the amount of solute that could potentially absorb the light. And then finally, remember that the cuvettes don't have to be full, so don't fill them to the brim. 3/4 full is plenty, and that's usually about 2 to 3 milliliters of your solution. So I hope that all makes sense. I look forward to doing some spectrophotometry with you, and I'll see you in the lab.